My name is Pavel. I work at Align Technology, and today I want to talk to you about type erasure and in conjunction with a technique that allows you to dispatch data from abstract structure to function parameters in C++. So what is type erasure? One variant of type erasure is, variant is a discriminated union where you can hold an object of a type from a closed set one at a time. So only one object of one type can be held at one time. And so you can put, for example, an int into our discriminated union. And we can ask this variant if it holds an int, and if it holds, we can get an int from it. And also we can apply visitor pattern to visit all possible variants that our discriminated union holds. Another type, another flavor is std_any that can hold literally any type. And in this example, we define our own type, my type, that is that std_any knows nothing about, and we can put an object of this type, and we can get our object back if we guess right the type that our any holds. This is type erasure of objects, and the next flavor is type erasure of functions of function objects. So we have the function that wraps and holds some kind of callable object or function. It can hold a function, it can hold a closure object from lambda, and it can hold a functor object, which is very similar to closure object, or rather the other way around. The closure object is very similar to functor function object. And so the basic idea of this talk is that we want, upon receiving a message that describes some request, for our magic to pick the right handler and to pass fields from that message to the appropriate arguments, function arguments in our handler. Let's go through what we are going to discuss today. We are going to discuss a straightforward and annoying way to do it in C++, how normal people do it, with an example in C#, the good technique where we unpack array into function parameters, a better technique where we unpack a dictionary into function parameters. By the way, array is an abstract structure and dictionary is not an abstract structure, but in our context, we assume that, dictionary is basically an abstract structure. Then we'll see what else can we do with it, and we'll try to automatically print descriptions of our API. We'll try to support optional parameters, support member functions, and contextualize our solution, so we can use it as context. So you will see a lot of code, surprisingly a lot of template programming, because, you can do anything without that, at least in this case, and, lots and lots and lots of code. We'll use Teo JSON. I like this library because it has a modern, very convenient interface, and we'll use this library throughout this talk. But of course, you can use whatever else you want or you like. Not necessarily JSON, but JSON is kind of very simple and accessible and understandable. So we'll use JSON in this case. Also, we'll use C++20 because we can. It is supported in pretty much all modern compilers. except to a lesser degree in GCC, at least in version 11. And also you can use this technique or approximation of this technique in C++ 11 to 17, of course. So you actually don't need C++ 20 to use it, to utilize it. So a little disclaimer, I know the difference between parameters and arguments, but this talk is already kind of hard, and I will probably use these terms interchangeably. And yeah, so annoying way to do it in C++. We have a number of handlers, and each handler receives a reference to JSON, to request in JSON format. So in the top of the slide, you can see that this handler doesn't need any fields from the request. So it basically has no parameters, and it contains just logic. In this case, we just print something to the console that we got the full request. At the bottom, we have a handler that needs one parameter, the parameter ID, and it has to extract that parameter from the request. This code at the bottom of the handler. And if our request doesn't contain that field, we report an error. And if that parameter, if that field is not of the expected type, we also report an error. And after we extracted the needed parameter and verified that everything is good, we can execute our logic, which is much more concise than the code for validating parameters. And again, we just print to the console that we got a var request and its parameter. Things get a little hairy, I'd say, when you have to have many parameters. So in this case, you have 3 parameters. Don't try to read that code. It's intentionally presented unreadable. And so this big part is the parameter validation, and that small part at the bottom is actual logic. This is unsatisfying, mildly speaking. So what can we do about that? We'll see it in a short time. So we also want to organize our handlers in a collection. We want to have a name for our request that is handled by the handler. And we have a type for handler, which is just a pointer to function. Then we have an array of tuples, which is our collection of our handlers. And next, we want to have a process request function or similar to that. So we can process a message using our collection of handlers. This is how it looks. At the top, we try to convert the message to JSON. If the converted JSON is not an object that we expect, we report an error. Next, we try to find the field request, which contains the name of the request. If request field doesn't exist, we report an error. Next, we extract the name of the request from that field that we found, and just logging to console that we trying to process a request with a given name. Next, we iterate our handler collection and trying to find a handler with a name that can process this message. And when we find such a handler, we just call that handler and pass a message converted to JSON. So basically, we are passing JSON. And otherwise, if a handler is not found, we just log that we couldn't find a handler for this request. I hope that's kind of straightforward. And next, we can write a program like this. And we get a result like this. So we're trying to process a request with the name Beth. And we have a handler associated with that name, and that handler is called, and it prints its output to the console. In this case, we got buzz request with given parameters. This is kind of okay. Let's see how normal people do it, and by normal, of course, I mean languages with rich meta information like C#. So we need to have an attribute which has a name that which holds a name that will associate with parameters. And here is our handlers, which do basically the same thing. They receive parameters. In this case, the parameters marked with attributes which set names with the parameters, and inside the handlers, these handlers, we basically just do the same thing, which is print something into console. Next, we have to have our process request functions, which receives a string. Next, we try to convert that string to JSON again. We try to get a property request, which is a field in the JSON, and get a name from that field. Next, we are trying to find a method in this program. So using meta information of this program, we are trying to find a method with the same name as the name of the request. Next, we have to arrange arguments for our method to call our method. And we do this by adding appropriate values from the JSON to the args list. So in the loop that iterates over methods parameters, we try to get the name of the parameter, of the given parameter that we're currently iterating over. Then we try to find a field with that name, and we are trying to add extracted value from that parameter with the appropriate type. That is, if the parameter is an int, we are trying to extract that value from the JSON node. Same for string, and if the parameter requires JSON node itself, we just return the node itself. And we then can invoke the method like this, passing arguments in an array. And eventually we can write a program like this, very similar to what we have seen, and we get kind of the same result, which is expected. So anyway, let's go back to C++, and let's think, what if we, instead of using dictionary, we pass parameters in an array. So we, instead of using like what usually people would use in the form of dictionary, will put all our parameters to our request in an array. And that means that the order matters, and we will be able to write our handler in C++ like this. So this handler receives parameters, typed parameters, not just the whole message. and can immediately use these parameters in its body. So this is, I think, an improvement. All the handlers now fit on one slide. And let's see what we need to do to support that. So again, we want to organize our handlers in a collection. We have string view as a name. We need to have some type as a handler, which we'll come back to in just a bit. And then again, we have our collection of handlers here, and we have our process request function. In the process request function, we need to change these 2 bits. So we try to find the arguments node in the request, and instead of passing the whole message, we pass arguments, just arguments nodes to each handler. So now we get to the type erasure part, and well, we need to somehow remember which function we put in our handler collection, and we need to somehow type erase those functions which have different arguments. And so you can try to convert a pointer to function to void star. This doesn't work, obviously. You can try to convert it using reinterpret cast, which is undefined behavior. So please don't do that. And one aspect of that is that it is not guaranteed that the pointer to object that is void star, the size of the pointer to object is equal to the size of pointer to function. And well, but we can convert using reinterpret cast one pointer to function to another pointer to function. And we'll use this fact, this is not undefined behavior, as long as you convert it back to the appropriate type of the pointer to function, and call it like in an unerased form. So to illustrate that, here are some examples of compilers and platforms that have different sizes of pointers to function and pointers to data. Although probably if you convert pointer to function to pointer to object, that is void star, it will work probably, but still, strictly speaking, this is undefined behavior. So please don't do this. And as a side note, there are APIs that return either pointer to object or pointer to function through void star, through pointer to object. And you're expected to convert it to pointer to function, knowing which entity you are trying to get. Strictly speaking, again, this is undefined behavior, although probably it will work everywhere. And the right way to do it is to return a union of pointer to object and pointer to function from a function such as getEntity. So you can convert the right pointer according to the type of entity that you're trying to get. Okay, so here is our handler type that we're going to flesh out. It stops being const export because we are using reinterpret cast in the constructor. So we can't make our initialization of our handler collection const export anymore, but we'll get to that as well. So in the constructor, we receive in our template constructor, we receive pointer to function with whatever arguments, and we with that pointer to function initialize our erase handler, our pointer to the pointer to function of this signature that is not receiving any arguments, because we can do that. This is definitely not undefined behavior. And next we have our handler2 implementation, which I will call our magic implementation. So it is initialized with a lambda that captures nothing, so it can be converted to pointer to function. And let's see. Oh yes, the last piece in here is the function call operator that receives pointer to JSON node that should contain arguments, and we just call our magic implementation, providing erased handler and pointer to a node with arguments. So let's see at our magic implementation. We here first things first unerase the handler, the erased handler, by basically reverse reinterpret cast. You can compare it to the reinterpret cast above that erases the handler. And next, depending on the number of arguments that we expect, we either just verify the arguments node and call handler. So we need to verify the arguments node so our system is strict considering which arguments can you provide. So if the arguments node exists, we have to verify that it is an array, and otherwise we report an error, throw an exception, and we have to verify that the array is empty because we are expecting 0 arguments. And otherwise also we report an error by throwing an exception. And after that, if the arguments node is absent, or if it is an empty array, we consider that the request is correct. The contract is met, and we just call the unerased handler. Otherwise, when we expect multiple arguments, we have to again verify our arguments nodes that it exists and that it is an array, and otherwise report errors. And next, we extract an array from the JSON node, and we are trying to verify that all the arguments are right, the types are right, and after that we can call our handler applying the arguments. So this is the validate arguments function. First thing we do is we have a constant that is the number of arguments that we expect. Next, we check if the provided number of arguments is equal to the expected number of arguments. If that's not the case, we basically log into the console that, hey, you provided invalid number of arguments. We're expecting this this number of arguments. So after that, we nonetheless try to verify each provided argument, because we want to give detailed error report to the engineer, so he can more robustly fix whatever code he's writing to send those requests. So we do that with this fault expression. We basically iterate over each argument, each expected argument. We check that this argument is provided, and then we validate that argument using validate arg function. It looks like this. We just get the argument I with index I from the array of arguments. We check that it is convertible to our expected type T. If that's right, we return true. Otherwise, we report that this argument is invalid and return false, therefore failing the validation. So is convertible to looks like this. So we can get a variant from our JSON node, and we can apply visit to that variant. And basically, for each type, we check that the actually contained type can be converted to our expected type. So we have Boolean, we have floating points, integrals, and all other types that we consider separately. In this case, this fancy form doesn't work with GCC as of 11.2 and doesn't work with Clang 12, although it is fixed in Clang 13. This works in MSVC, in latest MSVC, so you don't have to worry about it. So basically, this is, we are using contracts, floating point and integral in this case, and using that to provide provide a visitor for these types that are contained in the variant. So for example, float and double will fall into floating point case, and all other integers will fall into integral case, and so on. So you can rewrite it, try to rewrite it to run in Clang 12 by using generic lambdas. In this case, we basically, instead of using concepts in the argument definition, we define a template type, template parameter that is constrained with concepts. So if you want to use it with current GCC or earlier GCC, obviously you need to rewrite it in a more boring, I would say, fashion to expand maybe every type instead of using generic lambdas or concepts. Anyway, here is the report on the dark function that with which we report that this current argument is of invalid type, the unexpected type. In this case, we say that argument number I plus 1, so it's a one-based indexing, has a type that is contained in the variant, and we are expecting type that is expected type. And we use getTypeName function to get a string representation of types. So here's how it looks. Of course, pattern matching would be very useful here, but oh well. So we have conversion from for Boolean, for integer, for floating points, for strings, in this case, for std string and string view, for arrays, that is a special array type that is contained within JSON value nodes. And we can have objects, of course, that is the JSON value type itself, and object type that is contained, can be contained within JSON value. And also we handle unknown case that we didn't prepare for, so to speak, and we just return unknown type for all unknown types. And of course, we have our overload for receiving a variant from which we can calling inside the visitor the other version of the function to convert the type into to the string. So here we are, we validated arguments in our magic implementation. And next we want to call our handler applying all the arguments. Here, how we do it, we have to have an apply impl functions for our convenience, which receives which receives pointer to unraised pointer to handler, which receives a vector of arguments, our array of arguments, and which receives index sequence with basically a sequence of numbers that we can use to how do you say it in English? Unfold our template parameters, variadic templates, to use our variadic templates to unfold all the arguments to pass to our handler. So we extract from every item in the arguments array a value that can be then passed to our handler as parameter, as an argument. And we do it with this helper function that extracts for us the appropriate type. If the expected type is JSON value, we just pass the argument that we get, the parameter that we get in these functions, that is v. And otherwise, if this is some other type, like Boolean, integer, and so on, we call as t, which extracts the right object of the right type for us to pass to the handler as argument. And here is our convenience wrapper function that basically calls the implementation and provides index sequence to it in a proper way. And so finally, we can have all our handlers that receive parameters in an ordinary C++ fashion. And we have our handler collection, and we have our process request function. And we can write a program like this, and we get this output, which says that, well, the expected number of arguments is 3. Well, you provided 2, and argument number 2 has an expected type. We are expecting a string, while you providing an integer. And the whole processing of this request fails. We can fix it using that insight from that error reporting, and we can provide proper arguments, and we get the appropriate output from this program. I think this is not bad. Can we do better? What if we get back from the array of arguments into dictionary, which contains each argument as a name value pair? So we actually can do this in C++ in a fashion like this. So we associate using this template a name basically with type of the param. And so we will use C++20 because we can, and it will look like this. But you can use C++11 or through 17, though in a bit janky way using macros, but basically it will look almost identically to the C++20 case. And so C++20, we have a literal type. That is, we can use this type as a non-type template parameter. It has an array of characters in which we'll hold the name that we want to associate with the parameter. And we have a constructor that basically copies the array that we provide into the internal storage, which we will use then to get the names. And yeah, it can be used like this as a template parameter, non-type template parameter. And it can be instantiated like this, like at the bottom of the example. And so here is basically it. We have an alias for the value type, and we have a const reference to value through which we will pass basically parameters, values in parameters to our handlers. And we have a static function through which we can retrieve names for the parameter, for the particular parameter. So it looks like this. I think this is much cooler than the case before. For each parameter that we have an association of a name and the type for that parameter. And in the bodies of our handlers, we can extract values for particular parameters, and also we can use names of that parameters, of those parameters. So basically, we employ don't repeat yourself like rule here, and we don't have to repeatedly copy paste parameter names if you need to. So you can basically ask the parameter itself for its name. And we have to go back to our handler type. This time the constructor, also not const expr, it receives a pointer to function, but we constrain argument types in a way that only our parameter types can be used as parameters. So here we say that if all the arguments are parameters with this help template, then we allow this handler and constructor to be called and handler to be constructed. Otherwise, we forbid it. So next, again, we have our erased pointer to erase handler, which we initialize by reinterpret casting the actual handler to our pointer to function that receives void, that receives no parameters. Again, we have pointer to our magic implementation that is initialized with a lambda. And again, we have our function call operator that this time receives the request, the whole request, so not just some field like array of arguments. And we handle the whole request in our implementation. So let's look at the implementation. Here it is. It's much more concise than the previous one because we don't have to validate our array of arguments. We just ensure that the request has all the fields necessary to apply to our handler. And as before, we unerase our erased handler to the appropriate type. That is the reverse operation of the reinterpret cast that you can see above. And in case of 0 arguments, we just call our handler. And in case of multiple arguments, we validate arguments and then apply the arguments to our handler. The validation function looks also simpler. We just have basically a fold expression that validates each arguments against the request. And here how it looks. We try to find a field in the request with the appropriate parameter name that we get from parameter type. So if such field, such value is not found, or it is found but has the value null, we report that the parameter is missing because we consider absent parameter and null parameter the same as having no value. And we return false, basically failing the validation. Otherwise, we extract the type of the parameter from the param template parameter. So, we ensure that it is convertible to our expected type, the value node that we found. And otherwise, we report that the argument is invalid. And this time we say that parameter name instead of index has unexpected type, and we expect this using get type name functions as before. But the big difference is that we don't use indexes here because we don't have an array of arguments, and we use the name of the parameter itself. So after validation, we apply the parameter from the request and call the handler. Here's how we do this. This is also kind of simpler than we saw before. And here we again unfold all the templates parameter pack to basically functional arguments. And we use this function as a helper, get as. And for each node that we try to find for the concrete parameter name, we return basically this node if the expected parameter is a JSON value, and otherwise we call as t, where t is the expected type. And this way we extract all the arguments from our request and pass it to our handler. So again, we can have our handlers like that. We have our collection of handlers. We have process request function, which is curiously identical to the first one, which is from the annoying, straightforward and annoying way to do it. And we can write a program like this, and we get output like this. In this case, we can see that for parameter count, we passed a string, and our handler expects an integer, and also parameter ID is missing. And so the whole processing fails on the account that our request is malformed. But again, we can fix it, and we get output like this, like you seen before already. So what else can we do? We can use optional parameters. And in this case, we basically straightforwardly write that instead of string view, we want to receive optional of string view. And in the handler body, we can use value that will be an optional of string view. And basically outputs that the parameter is absent if the optional is empty, and otherwise print the parameter's value if the parameter is present. So we need to adjust a couple of things to handle optional parameters. In this case, we already had our primary template, and we have to have a specialization of that template for optional T. And in this case, basically, we have our alias as optional T and our value member also as optional T to pass arguments through that member. In the validate arg function, we also have to make a few adjustments. We have to add this if constructor. So in the case the value doesn't exist in the request, or its value is null. But if the expected type is optional, we consider this a normal situation and just return true. So again, using the template is optional for convenience, and defining inline variable also for convenience, for our convenience. And yes, here we have to basically duplicate what we had before, because we are extracting the actual type from the parameter and from the optional in a bit different way. I'm sure this can be written more elegantly, but for the purposes of the slides, copy-paste is good enough, I think. So this is basically the clause that handles optional parameters, and it extracts from the parameter type and from the optional type the type that we want to validate against. Again, we check that the type provided is convertible, and otherwise report that the request has invalid argument type. The function getAs that is used to extract actual values to pass to the handler, we have to have this clause for optional types. And again, if value is present and its value is not null, we extract the underlying value that lives inside the optional and return an instance of an optional from this function to pass to the handler. Otherwise, if the value doesn't exist, and or rather the value of the in the request, the value of this field in the request is null, we consider that that parameter doesn't exist and return empty optional. Otherwise, if this is not about optional expected type, we do basically the same thing that we have done before. And so now we can have a handler that receives an optional type, and we so we can add it to our handler collection as easy as that. Here is our optional type highlighted. And we can write a program that tries to process a request that receives an optional parameter. And in this case, we see that we provided value null. And in the output, we see that the body of the request printed that this parameter is absent. The same effect can be achieved by just omitting the parameter from the request. And if we provide an actual value, non-null value for this parameter, we just see that the handler outputs that value. So what else can we do? It would be cool to automatically have textual description of the parameters of our handlers. So since we have the association of names and types anyway, we should be able to have that. And so let's get back to our handler type. We can add a pointer to an implementation that prints or otherwise outputs somehow the description, and which is also initialized with a lambda, and we have print param description member function that for security reasons just exposes that functionality by calling the pointer to function. So here's our implementation, not so magic this time. So for the case of 0 parameters, we just output no parameters in the console. And for multiple parameters, we basically output information for each parameter in this fault expression separated by comma operator. And here is the function that outputs the description for each parameter. We, for our convenience, make an alias to the parameter type. We output the name of the parameter. We, in case of if the parameter is optional, output the underlying type of the parameter, and also output that this parameter is optional. And otherwise, we just output the name of the parameter. And so we can, again, organize our handlers in a collection. We can have print descriptions function, which iterates over the collection, and for each handler prints the name associated with the handler and calls the print param descriptions function for that handler to print its parameters, basically. And we can write a program like this, which outputs something like this. And I personally think this is pretty cool. So we can have automatically generated textual and maybe not even textual description of our parameters, of our handlers. So let's recap so far. What profit do we get? We have virtually no boring manual code to parse arguments within handlers. This is a plus. This is a big plus. We have automatic, consistent, detailed error reporting regarding arguments. So if we provide value of unexpected type or we omit the required parameter, we get automatically generated error report for that situation. It is very easy to add new handlers with various parameters because we don't have to add manual code to parse every parameters, and we can just use declare the parameters with the names associated with the types of the parameters. So because we can do that, we have automatic generation of descriptions, and actually implementation of request data structure can be abstracted. So it's not necessary that you can only use JSON, and this can be abstracted and hidden from handlers, and you can use actually whatever format the situation needs, be it XML or flat buffer or whatever else, and you can abstract that knowledge from the handlers. So handlers don't need to know the actual format of the messages. And so, yeah, what else can we do? We, of course, can type raise member functions. This is a bit more tricky because you can't reinterpret cast pointer to member function to pointer to function. And also, it is not guaranteed that the pointer to member function, the size of the pointer to member function is equal to the size of the function, the pointer to function. That is, one doesn't simply reinterpret cast pointer to member function to pointer to function. That's a mouthful. So there is one more nuance. So this time we'll use an array of bytes to hold the value of the pointer to member function. And you can just reinterpret cast your type unrelated to the array of bytes and use it like copying like here. This is undefined behavior. What you can do is memcopy the contents of the pointer to member function into your storage. And in C++20, instead of memcopying, you can use bitcast, which basically does the same thing. It copies the contents, the bytes from whatever you provided to the type specified as template parameter. And we'll use just that. So we have to get back to our handler type. And this time, the constructor receives pointer to member function instead of pointer to function. And yes, now let's jump straight to private section. Here we have a size, a constant for size of the member function, pointer to member function for the provided processor type. And we have an alias for our storage, which is just an array of bytes of the specified size. Here we have our storage, and here we have the pointer to the magic implementation that receives reference to processor, receives erased handler, and receives a request in the form of JSON value. So let's get back to the constructor. This is very similar to what we saw earlier. We bitcast the pointer to member function into our raised handler type. This is basically the reverse operation that we'll use. I mean, this is the direct operation that we'll use to the reverse operation that we'll use later that you see at the bottom. And here is our initialization of our pointer to magic implementation, again with a lambda that is converted to pointer to function. And this time it receives a reference to processor, it receives a raised handler, and it receives the request. And again, we unraise our raised handler with the reverse bitcast to the one that you see at the top. Next, we, in case of 0 arguments, we just call the handler. And in case of multiple arguments, we validate arguments and apply the parameters from the request, arguments from the request. And we do this with this function that also receives reference to processor and as well as unerased typeful pointer to member function, our handler, and request. And we, in the same way, unpack the expected arguments from the request and call our handler. So the last thing that is remaining is a function call operator for our convenience that wraps the implementation and receives reference to processor and request and passes it to our magic implementation with the erase handler. And eventually we can write a program like this. We have our processor type, which can have a state. And we have our handlers, which also can use that state that is contained in the processor type, instance of the processor type. We have a collection of handlers, and we have a process request function that is also receives a reference to processor. And the only difference is that besides receiving the reference to the processor, it passes this reference to the handler. And we can write a program like this. We have an instance of our processor. We pass our message and our processor to the process request function, and we get expected result. Attentive listener can wonder, well, you can do everything that we discussed with the std function, using std function. And that attentive listener is absolutely right. We can do that instead of when jangling with all that pointers and erasing and whatnot, we can just have a function that std function that receives reference to processor and request. We can, in the function call operator, just call that std function instance with processor and request. And yes, but the downsides or the nuances here is that std function can allocate memory, which you may or may not want. It has non-trivial destructor, which makes the destructor of handler non-trivial, and it can be made context concurrently, which for statically defined like handlers and collection of handlers, I would say is desirable. And so here is the whole implementation. We initialize our instance of std functions with a lambda, this time stateful lambda that receives and captures the handler, and basically otherwise does the same thing. So what else can we do? We can contextualization, I don't know how to say it, this whole thing. So currently this collection is const. Probably the compiler will not initialize it at runtime and will initialize it at compile time, because basically everything is known at compile time. But this is not guaranteed. So we would like to guarantee that our collection is initialized at compile time. So we want to make everything context. So the idea here is that we can pass the handler, that pointer to function or member function or whatever, as a non-type template parameter. We can do that. And we don't have to raise that handler, that value, and we can just basically bake it into the lambda. And we have to get back to the handler once again. We have to have function make handler, the template make handler instead of constructor, because you can't specify template parameters for constructors. So we instead have a static member function for this that constructs an instance for us. And in that function, we basically call the implementation, providing all the necessary information for that call for our convenience. You'll see that a bit later. Next, we have the default constructor, which is constexpr, of course. We have a function call operator that calls our magic implementation and passes reference to processor and request. And we have a pointer to our magic implementation. So in private section, also we have a constructor that receives a pointer to our magic implementation and initializes this the member pointer with that value. So basically, this is also for convenience, and here is the so-called meat of this class, of this implementation, which constructs a handler and initializes it with our magic implementation, which is lambda converted to pointer to function. And so here is our magic implementation. We have in the call our handler as non-type parameter, and also we receive in the make handler impl here. We receive the same handler just to conveniently get access to the types of arguments. And so we use all of that to just basically bake the value of the handler into the lambda. We don't need to erase and unerase the value of the handler. We just can straightforwardly use it and have our magic implementation like this. Also, I have to point out that we don't have anything other than the pointer to our magic implementation. So we reduced the size of our instance by 1 pointer. So we don't need a pointer to erased handler. And now we can constexpr everything. We can write, can initialize our collection of handlers as constexpr constant. And we can have this help function that you can see at the top, because we don't have to spell that long call out every time. But I personally don't like that in the definition in the middle and the bottom, we have some H, whatever. I don't like that we, so basically I don't like how it looks. So maybe we can return a tuple that is association of name and the handler from our helper function. And it looks like you can see at the bottom, which I also don't like because it changes the order of the name and the handler that we want to associate with it. So again, we can use our string literal as a non-type template parameter in our handler function, in our helper function. And finally, we can have something not as ugly as previously shown, and we can have pretty definition of our collection of handlers, where we have name and then associated pointer to function, like you can see at the bottom. So eventually we can write a program like this with the expected result, so it works. One last thing that I want to present to you is that we, of course, can have aliases for common parameter type. We can do it like this for parameter ID. count and payload, we can have aliases, and we can use this aliases in our definitions of handlers like this. And this is all I wanted to tell you about. I don't know what can be done in the future. Maybe we can use attributes and metaprogramming to do all that you saw in this talk, but in a like more proper way. Maybe using something like that, you can parse and generate schemas, or something like that for handlers at build time, or validate schemas, or something like that as well. And this is the end of my talk. Thank you for listening. You can watch my other talk about type erasure. This time it is about type erasure of objects. And yeah, thank you. Thanks to Timur Dumler for feedback that he gave me earlier for the draft of these slides. And yeah, you can find the slides by this link. Also, you can find demos there, or you can find demos directly by this link at the middle-ish of the slide.